so this is the chemistry lesson video for section 11.2, and this is going to be part 1 because this section, as many others, is kind of long, and so I'm going to break it up for you. So in section 11.2, we're going to talk about some of the general types of reactions. And so we're going to talk about 5. Just keep in mind there are other reactions that some we'll talk about later in this class, like acid-base reactions, neutralization reactions. Some you cover if you go into different chemistry classes, like oxidation reduction and things like that. So the 5 types that we're going to talk about are synthesis, decomposition, single displacement, double displacement, and combustion. Now, really quickly, depending on what book you use, sometimes synthesis will be called combination. And depending on what book you use, sometimes displacement will be called replacement instead. So like sometimes you'll see single replacement, double replacement. So it just depends on what you're looking at, but they work the same way. All right, so let's jump in and see what we learn about these reactions. So in a synthesis reaction, 2 or more substances react to form one product. So this is just a generic reaction of what it looks like. We have A by itself, we have B by itself, and what they do is they bond together as one. So now we have one product. So I like to say it's like a marriage. 2 people are separate, they get married, and they come together as a couple, and then they're one. So here's an actual example. Magnesium is by itself. Oxygen is O2, of course, because it's one of those 7 diatomic elements. That becomes very important in this section, are those diatomic elements. So we'll talk about those again in a minute. So magnesium is by itself, oxygen is by itself, and then they bond together. Now what I want you to notice, this is where people have trouble with this, is now oxygen no longer has the 2. Because once you bond them together, you need to balance your charges. All right, and so that's where people have trouble is, well, where did the 2 go? Well, remember, it's only diatomic when it's by itself. And so that's what a lot of people struggle with. People don't struggle with figuring out its synthesis. They struggle with the fact that I make you figure out what the products are going to be. All right, and then these are just some other examples down here of where we have, calcium and sulfur separately, and then they bond together. And then here's magnesium and nitrogen separately, and then they bond together. So that's what synthesis is going to look like. On a test or quiz, this is what you'll see. I'm not just going to ask you what type of reaction, I'm going to make you predict the products. So how do you know it's synthesis versus another type? It's going to be 2 elements. All right, because remember, it's 2 coming together to form 1. You can have more than 2 coming together to form 1, but in here we'll just have the 2. All right, so it says predict the products for the following reactions. The important thing to remember is that when you bond something, you have to balance your charges. That's like the most common thing people do wrong. All right, so it says we have copper and we have sulfur. Now normally I would look at the periodic table to see the charge of copper, but it's a transition metal. So if I give you a transition metal, I'll tell you what charge I want you to use. So I gave you the hint here, copper is a positive 1 charge. So I'm going to put my Cu, positive 1, well I just put positive, 1's understood, and sulfur. So if you look at the periodic table, hopefully you have yours labeled from previous lesson videos. And so remember, group 1 is positive 1, group 2 is positive 2. The transition metals are positive, but they can have variable charges. Group 13 is positive 3, 14 is positive or negative 4, group 15 is negative 3, group 16 is negative 2, group 17 is negative 1, and group 18, the noble gases, has a charge of 0 because they already have a full valence shell. So sulfur has a negative 2 charge. So what I need to do is I need to cross this 2 down. Now a lot of you have trouble with that because you think, well, Miss Borders didn't put a 2 on hers. Well, yeah, I didn't put a 2 on mine because copper's not diatomic. So why would I put a 2? You have to put your own subscripts when you make your products, when you cross your charges. So how do you fix it? Like, where did the second one come from? Well, once you're done, you go back and balance the whole reaction. So see, now I have 2 copper, so I put a 2 in front right here. So what that means is 2 coppers will bond with 1 sulfur to form Cu2S. So 2 come together as 1. All right? So let's look at our next one. So we have Be plus O2. So again, I want you to notice I put the 2 on oxygen because it's a diatomic. So when it's by itself, it exists in a pair as 2. All right? It doesn't mean it's going to have the 2 once it bonds with somebody else. So we have Be plus O2. So I start with my Be, And one thing I do want you to keep in mind, well hang on, I'll show you at the end because I just thought of something that I don't want you to miss. So BE, I would look at the periodic table, it's in group 2, so it has a charge of positive 2. Oxygen, see I only brought over 1, I did not bring over the 2. Oxygen is in group 16 and has a charge of negative 2. Positive 2 and negative 2 cancel, so I don't need any subscripts here. Alright, so then again, a lot of you bring the 2 over because you're like, oh gosh, well Miss Borders put the 2, I must need the 2. Okay, well I'll put the 2 on my side because oxygen's diatomic and it's by itself. On the product side, it's no longer alone. It doesn't need the 2 anymore. So how do you fix the fact that there's the 2? Well, you just balance it. So if there's 2 oxygens on this side, I just put a 2 in front. But now I have 2 beryllium, or 2 Be, so I just go back and put a 2 right there. Alright, so the thing that I just thought of that I want to tell you is I noticed the order that I just put all these in. Let's say that this one had looked like this. Like that. Let's say it had been O2 plus Be instead. And I know you're thinking, oh, isn't that the same thing? Well, yeah, it is, but a lot of you would miss it if I put it this way. So let's look at it. A lot of you would then put your answer like this. But remember, what are the rules? The rules are the positive one comes first. So even if I give it to you in a different order, you need to see it and think, oh, Be is positive, so Be is going to have to go first, and oxygen's negative 2, like that, and then you can go through and balance. Okay, so it doesn't matter what order they're given to you in, you have to list your positive one first. Don't forget those rules that we learned all the way back in chapter 7. See, that's the problem with this class, if you hadn't noticed, is you can never forget anything from previous chapters. Alright, so our last one, if you want, pause the video and try this one on your own. So I gave you iron, so of course that's transition metal, so I'm telling you to use a positive 3 charge. So I'm going to assume you paused it and tried it, and let's look at it together. So Fe, I've told you, is going to be a positive 3 charge. And sulfur, if you look at the periodic table in group 16, is negative 2. So I cross down my 2, I cross down my 3. And so then, of course, my last step is to balance. So I have 2 irons, so I put a 2. I have 3 sulfur, so I put a 3. Alright, and so that's all you do for synthesis. So the common mistakes I see in synthesis are people forget to cross the charges. That's the #1 thing right there. Second thing, you bring over diatonic subscripts just because I had them. That's also wrong. Third thing, forgetting to balance. Okay, don't forget to go back and balance the whole reaction, unless I state that you don't need to, but most of the time I want you to. Because, I mean, who doesn't love balancing equations? It's like one of my favorite things. Although one of my favorite things also is predicting products. I just think it's really cool to be able to tell what is going to happen in a reaction before I even see it. Alright, so the next type is decomposition. A decomposition reaction occurs when a single reactant breaks down into 2 or more products. So a generic reaction would be A and B together, and they split up into A and B separately. So they're together and they break apart. So if synthesis is like marriage, then unfortunately decomposition is like divorce. So here's an actual example. We have mercury and oxygen bonded together, and then here they separate. Okay, and again, you have to be careful of those diatomics. Oxygen doesn't have the 2 here, but when it's by itself, it does have the 2. Okay, so I'll remind you what those diatomics are in just a second. Alright, so here A and B is together, and then it splits apart. That's a decomposition reaction. Alright, so let's look at some. So before we start, let's look back at our 7 diatomics. Okay, I picked these 3 specifically to make sure you remember your 7 diatomics. So remember, you start at element number 7 and you make a big 7. So look at a periodic table right now. Element number 7 is nitrogen, N. So you go N, O, F, right across. ClBrI, straight down. So see, that makes a big 7 if you're looking at a periodic table. And then you have to remember hydrogen. Okay, so let's look at some examples. So we have water. Well, what 2 elements does water have? It has hydrogen and oxygen. So I know they're going to break apart. So all I have to do is ask myself, is hydrogen diatomic? The answer is yes. So I'm going to put H2. So see, I didn't put the 2 there because water has a 2. I put the 2 there because hydrogen's diatomic. Is oxygen diatomic? The answer is yes. So I'm also going to put O2. Okay, again, these 2's have nothing to do with the subscripts on this side. It has to do with the fact that these are diatomics when they're by themselves. All right, but the problem is, where did the second O come from? I need to balance to fix that. So since I have 2 O's on this side, I'm going to put a 2 here. But now I have 4 hydrogens, so I put a 2 there. And that's it. All right, so let's look at number 2. We have hydrogen and iodine. Hi. Hydroiodic acid or hydrogen iodide, depending on if it's in the gaseous form. So I need to split them up, hydrogen and iodine. So is hydrogen diatomic? Yes, it is. So it's going to be H2. Is iodine diatomic? Yes, it is. So it's going to be I2. So since I have 2 H's and 2 I's, I just need a 2 right there to balance everything. All right, let's look at our bottom one. We have ammonia, NH3. So I'm going to split up my nitrogen and my hydrogen. So is nitrogen diatomic? Yes, it is. So it's going to be N2. Is hydrogen diatomic? Yes, it is. Some of you, you've gotten used to the fact that you can put a 2, but then when you get here, you still feel like you can't change a subscript. Remember, it's just a 3 on my side because it's bonded with nitrogen. On your side, it's not bonded anymore. All right, so I'm going to change that to H2 because when hydrogen's by itself, it's diatomic. So then last step, of course, is to balance it. So here I have 2 N's, so I'm going to put a 2. Now I have 6 hydrogens, so what times 2 gives me 6 of 3. Now, I picked ones that were only diatomic related, just because I wanted you to really get the idea of diatomics, but not all of them are going to be. So I'm just going to throw up another one just to show you that they don't all have to be diatomic, because I don't want you thinking, sometimes y'all will pick out these patterns that you feel like you can find in my notes, but really it was just an accidental pattern that I did. So I don't want you just assuming when everything breaks apart it's always diatomic. So here, I'm going to give you one. All right, so pause the video real quick and try this one. All right, I'll assume you've done that, so let's go. All right, so gold and chlorine. Gold is not a diatomic, so when I bring it over, I'm just going to put AU. Chlorine is a diatomic, so I'm going to put Cl2, and then I'm going to go back and balance it. Remember, when we balance, how do we fix a 2 and a 3? We find that common factor. They can both become 6. So 3 times 2 gives me 6. 2 times 3 gives me 6. And then I just have to look that I have 2 gold right here, so I need 2 right here. Okay, so not all of them are going to be diatomic. I just really wanted to force you to remember what they all are. All right, so let's move on to our next type. Common mistakes on decomposition, of course, are forgetting the diatomics. Whoop. All right, so our next type is single displacement, or single replacement, depending on what book you're looking at. So a single displacement reaction occurs when one element replaces a second element in a compound. So in single displacement, you have something paired, bonded together, and then you have something that's single or alone. All right, so on both sides. So here A is single, B and C are together. Here B is single, A and C are together. Okay, so it's like in a relationship when, you know, like here's a relationship example. Okay, so this guy and this girl are together, but this guy walks by and she likes him a little bit better. So she's like, you know what, I'm going to break up with you and I'm going to start dating him. And so see, the thing is, somebody is single on both sides. So there's going to be an element on both sides. So here's an actual example. So here we have zinc by itself, and copper is bonded to nitrate. On the other side, copper is now by itself because zinc has bonded with nitrate. Okay, so what happened is zinc said, I'm going to bond with nitrate, and copper gets kicked to the side. Okay, so something is single on both sides. That's important for recognizing what type of reaction, especially once we then talk about double displacement. All right, so let's look at some examples here. So it says, predict the products for the following reactions. Now the important thing to remember about single displacement is the charges. A positive and a negative have to bond together. 2 positives can't bond, 2 negatives can't bond. So what I like to do is on the reactant side, just go ahead and write the charges. So that way you know who's going to swap places. Even if they don't technically have a charge right then. Like Br2, when it's a diatomic, it has no charge at that point. It's not made of ions, it's sharing electrons. But what we're going to do is we're going to write the charge of what it will be when it becomes an ion. So Br, of course, is -1 because it's in group 17. Na is +1 because it's in group 1. And iodine is -1 because it's in group 17. So what this means is Br has to bond with one of these because it's not going to be by itself anymore. It's tired of being by itself. So who is it going to bond with? So since Br is negative, is it going to bond with positive Na or negative I? That's why I tell you to go ahead and write the charges. Because it can't bond with negative I, they're both negative. So that means Br is going to bond with Na. But who do I write first? It doesn't matter that Br is first in the reaction because who comes first? The positive. So I'm going to write Na, and it's positive, and then you can just bring the charges over. And then Br, remember, I'm not going to write the 2 because it's not by itself anymore. It's not diatomic. So I'll bring over Br negative. So do I need subscripts? No, because the positive and the negative cancel out. And then who's left by itself now? I is. So then you have to ask yourself, is I a diatomic? Yes, it is. So it becomes I2. All right? And so then last step, of course, is balance. So I have 2 Brs here and only 1, so I needed 2. I have 2 Nas, so I needed 2. And then I have 2 Is and 2 Is. All right, so the thing about single displacement is figuring out who is that single one going to bond with, which ion is it going to bond with. Remember, opposites have to attract. All right, so let's look at number 2. So number 2, I gave you Fe, which is transition, so I'm telling you what charge to use. It's going to be +3. Now, lead, Pb, can also have multiple charges, but I didn't tell you what the charge is because you can figure it out since it's bonded to something. So you may want to get your polyatomic ion sheet out. If you need one, there is one on my website, or you can just Google it. I did not create the polyatomic ions, so you can find them anywhere. NO3 is nitrate. It has a -1 charge. But there's 2 nitrates. So instead of -1, it's really -2. So what cancels out a -2? Lead having a +2. Okay, I wrote the -2 up high because I don't want you thinking that's the charge of nitrate. That's just the charge of 2 nitrates. All right, so once we know this, who is Fe going to bond with? Positive Pb or negative NO3? Well, since Fe is positive, it has to bond with negative NO3. All right, so who do I list first? The positive one. So I'm going to come down here because I didn't leave myself enough room. So Fe is +3. NO3 is -1. Now some of you may be thinking, wait a minute, where'd that 2 go? Well, remember, this 2 is only here because Pb bonded with it. Remember how we would cross our charges? So this 2 is because Pb had a +2 charge. Well, it's not with lead anymore, it's with iron now. So what does it need now? Well, since iron has a +3, it needs a 3 now. You're going to have to get used to changing subscripts that I give you. It's a 2 on my side, but it's a 3 on yours. So now who's left alone? Lead. Is lead a diatomic? No. So I just write Pb. All right, and then the last step is to balance it. So I have 1 Fe, 1 Fe, 1 Pb, 1 Pb. I have 2 NO3s and 3 NO3s. So since I have 2 nitrates and 3 nitrates, remember the easiest thing to do with a 2 and a 3 is make both of them 6. So what times 2 gives me 6? A 3. What times 3 gives me 6? A 2. But now I have 3 lead, 3 Pb, so I put a 3 here. And now I have 2 iron, or 2 Fe. So I put a 2 there. And that's it. All right? So maybe pause the video and try the bottom one. And then I'll assume you've done that. So let's go. All right, so zinc, I told you is going to be +2. Hydrogen is in group 1, so it has a +1 charge. And SO4 is sulfate. If you look at a polyatomic ion sheet, it will tell you that has a -2 charge. So zinc is alone, so who's it going to bond with? Well, it's a +2, so it can't bond with hydrogen because that's positive. It has to bond with sulfate. So who do I list first? The positive one. So zinc is positive 2, sulfate is negative 2. Now one thing I do want to point out is that some of you may be thinking, whoa, wait a minute, why'd you pull that 4 over? Because I thought you said don't pull it over. Well, remember, I'm pulling the 4 over just like I pulled the 3 over here. It belongs to the polyatomic ion. So if you have trouble with polyatomic ions, which many of my students do, polyatomic ions in chemistry are like fractions in math. It's like some people get them and some people don't, and when you don't, it's just terrible. So these are our fractions in chemistry, is polyatomic ions. So if you have trouble figuring out when to bring something over, when you see a polyatomic ion, just circle it. If you circle it, you have to bring over what's in the circle. Okay, so SO4 is the polyatomic ion. Sulfate is SO4. NO3 is nitrate. Now this 2 is just telling me how many I have, so I don't necessarily bring that over. But if it's something that, a subscript that belongs to a polyatomic ion, you will bring that over. Alright, and so now who's going to be left alone in this scenario? Hydrogen. Is hydrogen a diatomic? Yes, it is. So I put H2. And then the last step is to balance it, but if you look, this one's already balanced. Alright, so the hardest part on single displacement is figuring out who's going to bond with what, so make sure you put your charges. Don't forget to cross charges. And then sometimes polyatomic ions start screwing people up, so just be careful with those polyatomic ions. I love polyatomic ions, so sorry, I like to put them in lots of things. We use them a lot in lab too, because they make for some cool reactions. Alright, so the next one that we're going to talk about is double displacement. Double displacement is very similar to single displacement, but instead of having a single element on both sides, everybody is bonded together. So a double displacement reaction involves the exchange of 2 positive ions between 2 compounds. So here we have A and B together and C and D together. But what's happened is A and C have swapped places. So now A is with D and C is with B. Alright, so here's a real example. We have sodium and cyanide, and then hydrogen and sulfate. But what happens is sodium and hydrogen swap places. So now sodium is with sulfate, and hydrogen is with cyanide. Alright, so this is an example if you've ever seen the show Wife Swap. Okay, so a man and a woman are married, another man and another woman are married, and then the 2 wives swap places for like a week or something, and it's supposed to, you know, be weird because they pick 2 families that are totally different. I don't know. If you've never seen it, I'm not suggesting you watch it, but that's what it's like, is Wife Swap, if you've ever heard of that show. Alright, so on this type, I would again recommend writing your charges first. Okay, so calcium is in group 2, so it's positive 2. Bromine has a -1. Silver is transition, but if you look at a polyatomic ion sheet, NO3 is -1, so silver has to be a positive 1. All right, I'm just going to circle my polyatomic ion so I remember that I need that 3. All right, so remember, the 2 positives are going to swap places. So I'm going to take calcium and silver, and I'm going to swap them. So that means calcium is now going to be with nitrate. So I'm going to put calcium first because it's positive. Ca positive 2. Nitrate is negative. And then I'm going to balance my charges. So I need to bring my 2 down. So I'll put parentheses in a 2. Alright, now silver is going to be with bromine. I'm going to write silver first because it's the positive one. So I write Ag positive 1. Now remember, bromine does not just naturally have a 2. It has a 2 because we were balancing charges with calcium. It's not with calcium anymore, so we're not going to bring over the 2. I brought over the 3 for nitrate because that is part of being nitrate. If you're nitrate, you're NO3. Alright, when you're bromine, if you're by yourself, you're Br2, but if you're bonded with somebody, you could have any subscript. Okay, I mean not any, but you know, you could have lots of different subscripts. Alright, so we're not going to bring the 2 over. So Br is -1. So since it's positive and negative, Br doesn't need a subscript on this side. And see, that's what a lot of you just have trouble with. Like, you don't understand, like, why. Well, remember, it has a 2 here because it's with calcium, which has a positive 2. Here, silver only has a positive 1. So 1 bromine will cancel out that charge. All right, and so then the last step, of course, here, I'm going to erase some of this just to make it a little bit easier to see at this point. Last step is balance the whole reaction. So I have 1 Ca, 1 Ca, 2 Brs, 1 Br, so I need 2 right here. I have 1 Ag, 2 Ag, so I need 2 right here. And then 2 nitrates and 2 nitrates. And that's it. Double displacement is the hardest for most people because there's so much going on. If you're not good at balancing charges, you're going to have trouble. If you don't understand polyatomic ions, you're going to have trouble. If you can't figure out what charge something has, you've already been having trouble. All right, so make sure that if you're having trouble with crossing, balancing charges, or charges in general, go back to chapter 7. That's when we first cover that kind of stuff. All right, so let's look at number 2. So Fe is transition, so I have to look at S to figure out the charge. So sulfur has a negative 2 charge, so what cancels out a negative 2? Positive 2. So Fe is positive 2. Hydrogen's in group 1, so it's positive 1, and chlorine's in group 17, so it's a negative 1. So remember, for double displacement, I'm going to swap my 2 positives. All right, so now Fe is going to be with Cl. I'm going to write Fe first because it's the positive one. So Fe positive 2, Cl negative, and see if you'll go ahead and write your charges, then you can just pull them over. Can charges change during a reaction? Yes, they can. But I'm not going to give you any reactions like that because there's no way for you to know if it's going to change. So in all the reactions I give you, I'm going to give you ones where the charges just stay the same. All right, so to balance my charges, I need to bring my 2 down. All right, and now we have hydrogen and sulfur that are going to bond. So I'm going to write hydrogen first because it's the positive one. So H positive and S negative 2, and then I'm going to cross that 2 down, just like that. All right, so last step is to balance the whole reaction. So let me get rid of some stuff. So we have 1 Fe, 1 Fe, 1 S, 1 S, 1 hydrogen, 2 hydrogen, so I'll put a 2, and 2 Cl, 2 Cl. And that's it. All right, so try the bottom one. Just remember, if you have trouble with polyatomic ions, I would circle this, and I would circle that. All right, so try this one, and I'll assume you've done that, and let's look at it together. So Na is in group 1, so it has a positive 1 charge. OH is hydroxide, it's a polyatomic ion, it has a negative 1 charge. Fe is transition, so we have to look at what it's bonded to. NO3 is nitrate. Nitrate has a negative 1 charge, but we have 3 of them, so that's really negative 3. So what cancels out a negative 3? A positive 3. So iron is going to be positive 3. All right, so I have all my charges. So what happens in double displacement? The first 2, the positive ones, swap places. All right, so now Na is going to be with NO3. I'm going to write Na first because it's the positive one. So Na, NO3. Now, am I going to bring the 3 that's inside the circle over? Yes, I am, because got kind of crazy there. Because to be nitrate, you got to be NO3. But why did I not bring this 3 over? Well, this 3 is here because it was bonded to Fe, which had a positive 3 charge. It's not bonded to Fe anymore. So I'm not going to bring this 3 over. All right? So it's positive and negative, so it cancels, so NO3 doesn't need a subscript. So now Fe is going to bond with OH. I'm going to write Fe first because it's the positive one. So Fe positive 3, OH negative 1. So I need to cross the 3 down. Now this is a common mistake for hydroxide. Because it doesn't already have a subscript, a lot of you put this. However, what do we know when we need to add a subscript to a polyatomic ion? We have to put it in parentheses, even if it doesn't already have its own subscript. Okay, so hopefully you put it in parentheses. All right, and then last step, of course, is just to balance. So here, let me just erase some stuff to make it a little bit easier. These kind of get a lot of stuff written on them when I'm doing them. All right, so we have 1 Na, 1 Na, 1 OH, 3 OHs. So I need to put a 3, but let me go back and fix Na real quick. So now I have 3 NAs, so I'll put a 3. Fe, Fe, 3 nitrates, and 3 nitrates. All right, so that's going to be the end of the first part of this lesson video. So just watch the second part because I'm going to cover combustion and kind of review all of these one more time.